this. All right, let me just repeat that we these two completed these two objectives. We know now the relationship between the force and extension. We did that in an experiment and we saw that in the formula, whereas the force increases, the extension increases, right? And we also solve problems using Hooke's law. Okay, moving on, we just want to go back through. Remember, if you have any questions, just feel free to stop me, right? So when a force is exerted on a rubber cord, it will deform by stretching. So this force causes an elastic force or a tensile force. Tensile force meaning that it acts along the length of the wire, and the act of stretching is a resultant of the attractive forces between the molecules. I spoke about this, and the objects that actually show these are like rubber bands and springs. So Hooke's law states that provided that the stretching force does not extend beyond the spring's elastic limit. Who remembers this word right here? You can send it in the chat or you can use your mic. Who remembers the elastic limit?
The
Me,
elastic limit
me,
is
sir,
how
me, sir.
far.
All right, you can go ahead.
I need once.
The elastic limit is how far the rubber band can stretch and before it starts to deform.
Before it starts to deform. So that's a good answer, right? All right, so that means that we can move on, right? So as the load of the spring doubles, the extension on the spring will also double because the extension on the spring is directly proportional. We spoke about this yesterday, right? Remember? Directly proportional, inversely proportional, right? And this law is obeyed until the limit of proportionality, which we just spoke about is the elastic limit. All right, so the law is obeyed until the limit of proportionality is reached. So basically, the material will become permanently deformed and no longer applicable to Hooke's law if it doesn't go to its original length, right? So if the elastic limit is stretched beyond the elastic limit, it will not return back to its original length, right?
Sir, yes, Stephen, sir.
Go ahead.
The spring would have more. The spring would have more important in a hook slot than a rubber band because the rubber band, the rubber band can come back to size.
Well, not necessary. If we test it and we have remember that a rubber band can actually we have cases where rubber band it can wear out and it can even burst. So it can so it
Yeah.
passes its elastic limit. Mhm. And we're okay now. Everybody is okay. No more
Yes.
questions.
Yes, sir.
Go ahead. Okay. All right, let's move on. So yeah, we spoke about this. This is the original length of the spring. We stretch it, it will return back to this original length if we let it go. And this is another length, right? If we stretch this, it can return back to its original length. But if we stretch it beyond, say, its elastic limit, say we stretch it down all the way down here, it will look something like this, right? It will look something like this guy over here. And we spoke about this yesterday also. This what somebody just wanna mention what this is again?
The limit, sir.
Yeah, the elastic limit. Perfect. So Hooke's law is applicable up to this point. All right, so we can continue, right? We went through these in class. Force F equal x k times x, right? And we said that in order for us to find the force, we need the mass and the acceleration due to gravity. This formula, right, is very useful.
Find
Um,
the excuse me, sir, to find the force, right?
Mm-hmm. Yeah, to find the force. This formula is used to find the force, right? And we went through this. All of these notes are posted, right? And this calculation is also posted on Google Classroom. We went through this yesterday. Just a recapping, we have our formula F times Kx, right? And we want to find the extension, right? We want to find the extension. We got this guy and we got this guy. We want to find the extension. So we transpose, right? We divided both sides by K. It came down to this. And we now need to find our force. So from our force, they said that the mass is 1.2 ton. When we look back on the formula here, in order for us to find the force, we need to times the mass of the object times the acceleration due to gravity. So this came down to 1.2 tons, right? And we converted this to what? What do we converted this guy to? Can I send it in the chat if you remember from yesterday?
Newtons.
No, we converted our mass here to what? From tons.
Tons.
From tons.
Newtons.
No, from 1.2
Kilogram.
kilogram. Right, perfect. Kilogram. Okay, right here. Right. Kilogram. And then we went ahead. See, it's over here. Converted
Just,
to kilogram.
excuse me, sir.
Go ahead.
During the formula, you must always convert to kilogram.
Yes. Whenever you're working with any form of any form of a science formula, right? You must always go to the SI unit, right? You went through SI unit already, right? So the SI unit for time is seconds. The SI unit for for mass is kilograms and so forth. And we got our final answer. We converted this so that it could be read easier. We if we have time, we're probably not going to be able to do this today, right? If we have time, we'll go back to standard form next week. Let me just write that down, right? Let's make a note of that we need to go to standard form next week, not this week, because this week you're just going to do this last question, right? You're going to do this last question and then just take a picture of it and send it to me. Send it to Google Classroom. So this, I'll post this in the group, or somebody can just post this picture in the group, and you can send it to me. It's very easy, right? We have our mass here, our mass, and we have our K, just like the last question, right? But there's a little difference right here. What is the difference here between this and the last question?
Sir, the mass are not grams, so it must
The,
be converted.
so the mass is grams, so we're going to convert the mass to grams. You probably want to write this down, right? Just write this down somewhere on a piece of paper or so. So we
You said
convert
mass, sir.
we convert the mass to kilogram. Anybody
Kilogram.
notice anything different? Anything else?
Sir, so we always convert
Right. Always convert your grams to kilograms. Always use kilograms.
grams to kilograms and kg, from ton to kg.
Yeah. Anybody notice anything else different? So the K
No
is
K
the
is
same.
there, sir.
Yeah, the K is the same.
Oh.
And
Oh.
you got it? What else is different?
So that Newton meter.
Newton meter? Yes, Newton per meter. That's the formula for our K, right? That's the formula for, that is the unit for our K. So this K remains the same. It's the same K over here. It's the same, similar K, 2.0 times 10 to the 5 Newton per meter. And then this guy is 2.5. So if we write down our formula, right, I'm just going to help you to start. If we write down our formula, right, kx, and we have our k, we have our k, what else we need? We need our force, right? How do
Yes,
we
sir.
go? How do we go about finding the force? Anybody remember?
Mass times gravity.
Mass times
Mass
gravity.
times gravity.
Perfect. So we have our mass of, you convert this to kg. Then now we have to do 2 at the calculation. Why? Because we have what?
It's on both on the moon and on the earth.
So we have to do 2 calculations. We have to find the extension on the earth and we have to find the extension on the moon.
On the moon.
You want to write this down, right? So you're going to do this for your just follow the same steps, right? You know, yeah, you put in a mass and you times it by the acceleration due to gravity, right?
Mm.
Acceleration due to gravity is 9.8. This the question. Remember, I told you yesterday. If the question tells you that it's 9.8, use 9.8. If a question doesn't specify, you can use 10, right? But you can round it up. But if a question specifically states 9.8, like this question, ensure that you write it down. Any questions, right? Before we continue?
So I'm right here, sir. I'm done right.
Okay. Just tell me when you finish.
So you have to go watch over the video.
Yeah, man. Yeah, that's why I post them. If you have any queries, you can just go back over, or remember you have my number, right?
Right then, sir.
You have my number. Text me in the day, preferably. If you need to text me in the night, you can go ahead and text me in the night. If I'm available, I will. All right. Don't text me then. Don't text me in the night. Nobody should text me in the night. See? Nobody. I don't want
That
any.
just
I don't
sound
want
right.
any messages in the night.
Uh,
I don't want to see any. If I see any messages coming in, I'm going to block you. I'm sorry, because I don't want any messages. Because somebody said that is why, right?
in a night, why, sir? But night day that
Yeah.
government.
Let me see exactly who is talking. If you're brave enough, let me know who is talking.
Malvern attack,
All
sir.
right. So I'm not accepting any messages from Malvern and user 2021. Well, I wouldn't know who that is, right? I'll figure
Alright,
it
you
out.
can skip back to your working out, sir.
Go again.
Skip back to your working out. So.
Right. You finished writing off? The person was writing.
This is going like class, Google Classroom, something, sir.
Go again.
This go in a Google Classroom.
Yes, this will be in Google Classroom. I'll take a screenshot of this and
Yes,
then
sir.
put it as an activity, right? After our class, I'll take a screenshot and then put it as an activity so you can do it,
Okay, sir.
right? No, we move on to the next matter at hand. I don't have a lot of time. We need to finish off simple pendulum for this week. I gave you guys until today. I only saw 3 assignments.
Sir, question. I have a serious question.
This box.
In the formula, sir, he said square. He said, let me look.
Sir, the gradient part, sir. Oh, you do that, sir.
Yeah, we'll go through that. I went through it in the video.
Yeah,
Where
but
He
last,
did not post that part on Google Classroom, sir. The graph part.
mm,
it was posted.
No, no, sir, it wasn't. It wasn't there, sir.
you know our video.
Tell me if this is what you saw. Tell me if this is what you saw. Give me a second. Is this what you saw on the Google Classroom?
Yes, sir.
So let's go through it, right? We have a table show the time taken for a pendulum to complete, why is this not working? Oh man. All right, to complete 20 oscillations, right? At different lengths. So we have the same thing we did in class, right? We have our length, and we
190.
increase it and we do 20 oscillations there. We went through this, and this is the amount of time it takes to complete 20 oscillations.
We all got that
Sir,
part.
just one of them, sir. Just one of them. Just one of them.
So we all that did that part. Sir.
Right. So
Graph.
I saw that coming in. I saw where you find the time of I saw the time for one oscillation, right? And I saw the period squared. But then the questions, no, the actually important questions is to first of all, of course, complete the table by filling in the values of period and period squared. Now the second part is to plot a graph of period squared versus length. You didn't see this?
Yes, sir. I saw that. That's why I'm asking, sir.
Mm-hmm.
And do that.
I did a formula T equal 2 pi square length.
Formula. All right,
Yeah.
let's just finish this part, right? And then you were supposed to, from the graph, find the
And the
gradient,
gradient.
and then I said I would do this in class. I would do this question in class, right? And then, of course, if you want, you can do this as well. But the most important thing was for you to plot the graph and to find the gradient. I said that in the class, in the group, right? And these are very easy, right? We'll go to them after. These two simple. This is what you would get on your multiple choice questions for CSEC. Where now we are preparing for CSEC fully. We're preparing for CSEC. Like whatever we're doing now, that's what you're going to get on CSEC. You are going to get a graph on CSEC. If you're serious about this exam, you're going to get a graph. So I really expected more students to come forward and to attempt the questions, attempt them, give them a shot, right? I really expected more students to come.
Sir, me do the graph about right?
No, still post it, still upload it.
I
Yes,
did
sir, but me
9,
send
sir.
you, me never know how to do, but me send you in your WhatsApp, sir.
All right, I'll look back through it. I haven't looked at my phone since morning because my phone
On Google Classroom.
crazy.
But you wanna say, cause I did say, you did go through your graph today.
Mm-hmm.
Probably. But me do everything else.
All right, let's see what we can accomplish today. All right. Let me just fix this.
Sir, I'll not answer my question, sir.
Go ahead.
Sir, how to complete one oscillation?
Oh, you never, Mr. Malvern, I didn't go back through the slide.
Brother, time times the number of oscillations. Time divided by number of oscillations.
All right, I swear I did this. I don't know why I did it. All right.
Where's the marker? A.
Time,
what?
like the seconds divided by number of oscillations.
All right.
Respect.
When you go do period square, that's
For square times. Square oscillation. One oscillation.
Okay, my friend. Much respect.
I said this in
So,
the
so 1.22.
Yeah, 1.22. Then I go square if you get periods.
I said this in the class. All right. Let's go through it now. I'm bringing it up now. So just give me a second. All right. One more thing. Fix this. Okay, we're set. We are set. All right. Just let me know if you've seen that, please. Are you seeing it?
Yes, sir.
All right.
Yes, sir.
So mm, I missed out. I missed out the values. This is the graph that I did. Right. We'll go to that in a second.
Question.
Yes,
Question.
sir. Go ahead.
Sir, the numbering, sir.
Yeah.
That's what killing everything. Numbering. You
No
can't.
problem. No problem. No problem. All right. So I'll bring up the actual values then. Let me bring up the actual values that I came up with. This might take a second. I did the calculations already. Simple pendulum data. Where is that? Oh, here we go. I did the calculations and then I'll show you to how to it's really difficult, guys. It's really difficult to teach this over online. It's more of a practical thing. I'm telling you the truth, right? It's more of a practical thing. It is very difficult to teach plotting the graph over the internet, right? It's a little challenging, but I am trying my best, right? And I'm going to ask you to also try your best as possible. Try and see what you can accomplish with the resources that you have, right? It's very challenging to teach this over the internet, honestly, right?
Do you even have no pencil?
Alright. So these are the values that I got. Let's paste them. This frees up on me now. Come on. No, not it. All right. All right. So we're asked. Just tell me if you're hearing this, please, or you're seeing and hearing. You can send it in the chat. Yes, sir. No, sir. Right. Are you seeing the shared screen? Well, we have less than 5 minutes. Okay, great. So for the first one, as I said, you can go back to your values, right? But to find the time for one oscillation, what we do exactly again? Find the time for
Times by oscillation. Number of
right. So
Mm.
24.49 divided by 20, and we get 1.22,
1.22.
right? And then we'll do the same for period squared. How we get period squared?
Square 1.22.
Yeah,
The
so
square, sir.
yeah,
1.10.
1.10.
1.10.
1.1. 1.48.
Oh, why this a man a
1.
1.48, dog? Why this a man a yo?
48.
Yeah, I think they're gonna run
48.
off it.
Yeah. So
Oh
about
crap.
that, approximately that, right? All right, we're moving on now to the next part.
Not really have
Um,
for
so this now, so we took out our important values, right? We took out our length and we took out our period squared. The question asks us to plot period squared versus length. And from the lecture that I did, I specifically placed period squared in the y-axis. So period squared and length will be down here, and you plot a graph, right? So we have our values 0 0.35, 0 0.5, 0 0.7, 0 0.9, and 1, right? And 1 right here, this guy right here. Now we need to be able to plot this. How are we going to plot this? Because we need to put length in this axis right here. So we're numbering our scale. We start at 0, right? And we end at 1. So you want to find increments that will help this. Say you can start at 0 0.1, 0 0.2, 0 0.3, 0 0.4, 0 0.5, 0 0.6, 0 0.7, 0 0.8, 0 0.9, and then you go up to 1. So graph will look something like this, right? So you want to find increments. As I said, it's very difficult to teach this over the internet and to take some additional work from you to be able to research this. You're going to have to be able to research this, right? But it's very simple. Once we practice,
Sir,
go ahead.
for the length, it's just from 0 to 1. Sir.
Yeah, from 0 to 1. So you're not really watching the 0 0.35 or the 5 or the 7 or the 9. You're watching, right? You're watching the range of values. So a range of values is from 0 down to 1. That's our range. So that's what we want to get. All of the values fall in between these two guys right here, 0 and 1. All of the values fall in between. So you want to get the range. You want to create a scale that can have everything on it, so that when you're actually plotting, you don't miss out any points. Better understanding?
Sir, so you say with a label from 0 to 1.
Yeah.
So in between them would be 0.35, 0.8.
Yeah, 5, 0 0.7, 0 0.9. But I'll show you another trick that will make your life very easier, right, as we move on. But I guess we're going to have to pause for a second and then come back, right, because we have less than a minute. We have less than a minute here. So we're going to pause and come back, right? So just use the same link and join back as soon as possible so we can start. How many persons? 14 persons are here. All right. I'm going to end it and then we'll come back.